Welcome back to another Forge College Explainer. Today, we're basically playing mad scientist. We are extending modular contracts without, completely blowing up our engineering lab. If you've ever tried to just bolt some new functionality onto an existing smart contract and watched the whole thing inexplicably crash and burn, well, you're absolutely in the right place. We're going to break things on purpose, analyze the wreckage, and then fix it perfectly.
To give you a quick map of where we are in the Solidity from Zero track, we just finished building our contract's brain with libraries in the last lesson. We successfully extracted those stateless helper functions to shrink our gas footprint, which was awesome. Now we're moving from splitting code up to safely recombining it. We're essentially bolting on new limbs right before your massive capstone project coming up next. Here's our blueprint for today. We'll be tackling the modular challenge, the storage collision catastrophe, the ABI mismatch mystery, the library versioning trap, and finally, getting you prepped for that capstone.
All right, Section 1, the modular challenge, or as I like to call it, bolting on the limbs.
So extending a contract isn't as simple as just slapping some new code onto it and calling it a day. You have to preserve the original public interfaces. Our lab experiment today follows 3 straightforward steps. First, we've got a base module that implements our core state. Second, we deploy an adapter to extend its functionality. And third, our ultimate goal, executing the whole new system smoothly without ripping the original contract apart.
Moving right along to Section 2, the storage collision catastrophe.
Okay, imagine trying to install a fancy new car radio, right? But instead of connecting it to the speakers, you wire it directly into the steering wheel's airbag sensor. That's essentially what happens when you blindly inherit a contract and mess with its internal wiring. Think of our base module having a simple integer called counter. But then our naive extension makes a fatal mistake. It redeclares that exact same counter variable. In Solidity, doing this creates a completely separate storage slot that shadows the parent contract. Suddenly, your getter function returns a highly misleading value, and your expected math progression totally ruined.
The absolutely crucial mental model to grasp here is this. Solidity lays out inherited storage sequentially. It is a very specific, serialized, and honestly, incredibly fragile grid. When you have multiple contracts reading and writing to this grid, preserving the exact shape of that storage layout is just as important as preserving your function signatures. Because if you disrupt that sequence, you corrupt the entire state, and there's no coming back from that.
So how do we fix this mess? First off, we have to stop inheriting blindly. The number one rule is simple: never shadow variables. But structurally, your best bet is using composition. That's where your extension simply holds a reference to the base contract, rather than inheriting it directly. Alternatively, if you really must use inheritance, use explicit single-owner storage structs. You have to treat your storage layout as a highly protected part of the module's public contract.
That brings us to Section 3, the ABI mismatch mystery.
To safely extend functionality without totally wrecking our storage, we often reach for an adapter. An adapter is a structural design pattern that essentially acts as a bridge. It delegates behavior from the extension back to the base module without tightly coupling them together. It's a beautifully clean way to add new operations, but it does come with a major risk if you don't wire the communications correctly.
Because there is definitely a right way and a very wrong way to build this bridge. If you use a raw, low-level call, assuming the base module has a function called bump, it is incredibly fragile. If the base module updates its signature later, this low-level call just fails silently. You get absolutely zero debug information. On the flip side, using a typed interface is much safer. By casting the address to a specific interface, the compiler actually guarantees typed calls. It catches errors immediately during compilation, or at the very least gives you clean, predictable reverts at runtime.
You should always remember this concept. Adapters are your translators. Think about it. If a translator just assumes they know the language but doesn't explicitly verify it, they're going to cause an international incident. So use explicit Solidity interfaces to avoid those silent reverts. Just don't rely on raw function selectors when a typed interface can enforce exact ABI compatibility for you automatically.
Let's jump into Section 4, the library versioning trap.
Now, this is the one where your code compiles perfectly fine, but acts entirely possessed at runtime. Imagine you've got a shared external math library. In version 1.0, your increment function adds exactly 1. Nice, predictable, safe. But later on, someone updates that library to version 2.0, where it increments by 2. If you forget to coordinate your deployed linkage, your contract suddenly starts acting like a haunted calculator. The logic diverges completely, and debugging it is an absolute nightmare because the bug isn't even in your contract's source code.
Thankfully, the elegant engineering fix for this is semantic versioning. You just add a tiny version getter function to your library. Then you force your adapter's constructor to explicitly verify this exact version before it allows any linking. You just write a require statement that checks the library's version, guaranteeing that the runtime behavior matches your compiled assumptions. It's such a simple addition, but it will literally save you hours of hair pulling.
Finally, Section 5, Capstone Prep and the Debug Report.
Now that we've cleaned up our chaotic engineering lab, we need to talk about how to document these fixes. For the upcoming Project Overview Capstone, you aren't just writing code. You are proving to us that you can engineer modular systems safely. You're going to have to produce a professional debug report containing these 4 exact elements: reproducible failing test output, a minimal reproducible code sample, a crystal clear root cause analysis, and the exact code diff that patched the issue. The good news? We've just walked through 3 perfect examples today of how to structure exactly this kind of problem solving.
So let's quickly recap our golden rules for extending modular contracts. Stick to these, and your code remains completely reusable and bug-free. Number 1, do not shadow storage. Prefer composition instead. Number 2, replace those fragile low-level calls with explicit typed interfaces. And number 3, always version your libraries to enforce runtime compatibility checks. The tools and the patterns are now officially in your hands. But the real question is, will your modular contract survive the ultimate test of the capstone deployment? I have a feeling they will. Thank you so much for joining this Forge College Explainer. To properly prepare for your capstone, grab those code snippets we discussed, and to explore even more Web3 engineering secrets, make sure you visit forge.college. We'll see you in the lab next time.